Today, we're diving into a lab that literally brings a piece of outer space down to Earth. We're talking about a place where huge spacecraft float on a cushion of air so they can rehearse for missions that are millions of miles away.
I know, it sounds like something straight out of science fiction, doesn't it? The idea of taking a massive, incredibly complex piece of machinery and making it act like it's in the total emptiness of space? But this isn't a movie prop. It's a real-world engineering marvel.
And this right here is the multi-billion-dollar question every space agency has to solve. Before you launch a priceless robot on a mission where there is zero room for air, you have to be absolutely sure it's going to work. So how do you possibly practice for zero-G when you're stuck right in the middle of it?
So here's how we're going to break it all down. First, we'll dig into the zero-G challenge itself. Then we'll look at a pretty brilliant solution that's basically a giant game of air hockey. We'll dissect the simulator's anatomy, meet its digital mastermind, and finally, see how it's all used to rehearse for actual space missions. Okay, first things first. Let's get a handle on why this is such a tough problem. Simulating microgravity isn't as simple as just making things float. It's about recreating the incredibly complex physics of how things move around in space.
For a long time, we've had a couple of main tricks up our sleeve. You've got parabolic flights, you might know them as the vomit comet, that give you a few moments of real weightlessness. Then there's neutral buoyancy, where astronauts train in these massive swimming pools. It's great for practicing movement, but the water drag can really mess with the delicate mechanics of a sophisticated robot. And when we say moments of weightlessness, we mean it. We're talking about 20 seconds. Just imagine trying to test a robot that's supposed to assemble a solar panel. In 20 seconds, it can barely get its arm out, let alone do a complicated job. It was obvious we needed a much better way to practice.
So how did engineers crack this massive problem? Well, they looked away from the cosmos and towards the local arcade. The solution, believe it or not, was inspired by an air hockey table.
And this is it. This is a ground test system for a multi-arm spacecraft laid out in a U.S. patent. The heart of it is this gigantic, perfectly polished marble platform. And on top of it, a spacecraft simulator just floats on a cushion of air, almost completely friction-free.
The technology is called an air-bearing system. And yeah, it works exactly like that air hockey puck. It uses a thin but powerful film of pressurized air to lift the entire simulator, which cancels out gravity's downward pull and lets it glide across the floor like it's on ice.
Just picture it for a second. A super high-tech lab, totally silent except for the hum of computers. And right in the middle, this complex robot, weighing hundreds of pounds, just glides around with the push of a finger. It is the closest we can get to the feeling of space without ever leaving Earth.
Okay, so that's the big picture. Now, let's zoom in and really look at the nuts and bolts, the actual hardware that makes all this possible.
The whole system really boils down to three core pieces. First, you've got the air-floating platform itself. Second, the spacecraft simulator that actually does the floating. And third, this very smart ceiling up above, which basically acts as the mission's playground.
And here is the absolute star of the show, the simulator. This CAD model shows you the central body and its robotic arms. Now, according to the patent, each arm has 7 degrees of freedom. That gives it a wild range of motion. Honestly, in some ways, it's even more flexible than a human arm.
So what are those super flexible arms reaching for? Well, they're reaching for this, the test truss ceiling. You can think of it like a configurable grid, where you can hang mock-ups of anything the robot needs to work on in space, like a satellite that needs a refuel, a docking port, or even these honeycomb structures for the robot to practice crawling across.
The hardware is seriously impressive, no doubt, but it's really just a puppet. The real magic happens inside the digital mastermind that's pulling all the strings.
So here's how a test actually runs. First, a quiet air compressor kicks in, pumping out 0.8 megapascals of pressure. For perspective, that's about 4 times the pressure in your car's tires. That's what makes it float. Next, a bunch of cameras on that smart ceiling track the simulator's every move. All that data gets fed into a central computer, which figures out what to do next based on the mission plan. And finally, it sends commands back to the robot's arms to get the job done. Perfect.
Now, I know this block diagram looks complicated, but you can just think of it as the system's digital nervous system. Information from the camera eyes to the computer brain, which then sends orders to the robotic muscles. It's this non-stop, high-speed feedback loop that makes every single movement so precise.
Okay, so we've got this amazing zero-G lab on Earth. But what's it actually for?
The answer is pretty cool. It's for rehearsing some of the most ambitious space missions we've ever come up with.
Using a system like this, engineers can practice a whole range of incredible tasks. We're talking about building massive structures in space, like a future space station. They can practice really delicate satellite repairs, like refueling or swapping out a broken part. They can even perfect tricky maneuvers, like autonomous docking, or having the robot crawl across a structure to get to its job site.
And this right here really brings it all together. On the left, you've got the test lab, the practice field. On the right, you have a mock-up of the exact kind of satellite it will one day be working on for real. This is where you work out every single kink so that when the real mission is happening, millions of miles from home, it goes off without a hitch.
In the end, it all comes down to this simple truth, which researchers in the field live by. When you're working in space, you don't get second chances. Those strict ground tests are absolutely essential for making sure the mission is a success and that everything is safe.
This kind of technology doesn't just let us test what we can do today. It lets us dream about, design, and safely rehearse what we can do tomorrow. Building massive telescopes in orbit, assembling ships to go to other planets, cleaning up space debris, all of it starts right here, floating on a cushion of air. It really makes you wonder, now that we can practice almost anything, what's the next impossible leap we're going to take?